Let's talk about complex numbers. Perhaps I would like to start with this equation f of x squared plus 1, and we are asked about to find the roots. That is where the function will cross the x-axis, and clearly we can say from the graph of our function, there will be no crossing on the x-axis. Does it mean we have no solution? Suspicious. But our friend Goss says, hey, humans, there is a solution, or else you will violate my fundamental theorem of algebra that says a polynomial of degree n has n roots. Before we go with the complex numbers, I would like to take you for a short discussion on how the numbers evolved from the set of natural numbers to having a complex number. From the ancient times, we devised a way to count things by natural numbers like 1, 2, 3, 4, 5, 6, and so on. We are also good and learn how to use the fraction or rational numbers to include all in between the whole numbers. As we progress, there is a need to find additional set of numbers that can describe death, loss, or decay phenomenon. Hence, the long journey for the acceptance of zero and negative numbers has started to many parts of the ancient civilization. China is the first to adopt the negative numbers, learning its application to depth. They say it's good for depth, but Greeks has a lot of reservation for zero. How could nothing be something? And Romans are shouting, numbers are lame, let's find something. And it was during the Renaissance that the acceptance to zero and negative numbers begin to emerge. European countries says we're okay, good for decay and depth analysis. In India and Persia region, zero and negative are good for this new algebra thing. And in China is shouting, hey, we're already using negative numbers 2000 years ago. We say it's good for depth. It was then followed by the discovery of irrational numbers and transcendental numbers. These are what we call the set of real numbers. So, let's go back to our problem f of x equals to x squared plus 1. Does it mean we really do not have solutions, or we are just missing some dimensions or set of numbers? The great progress in the math of algebra had pushed many of the mathematicians to find solutions to polynomial functions. It was also the time that mathematicians is earning money and fame by doing a math duel. The battle for solving the quadratic equation happened between Tartaglia and Ferrari, where Tartaglia dominated the duel. A mathematician named Del Ferro did the challenge of finding solution to a higher power, this time a cubic polynomial, and he is the first to discover the general formula for finding the cube roots. Through his definition of the pressed cubic in the form of x cubed plus cx equals d, but there is a limitation on his findings that c and d in his equation should be positive. Del Ferro kept this solution because it is an edge for him to keep his position as one of the great mathematicians during the time. He kept this solution until his near death and gave the solution to his student that is long looking for the solution of these cubic roots. The name of the student is Antonio Fiore, and upon getting the solution from Del Ferro, Fiore thinks that no one is working yet for the cubic roots, that he has now the solution. He turned into Tartaglia for a math duel of finding solutions to the cube roots. Tartaglia accepted the challenge and bluffing Fiore that he is already working on it. Hey, deal, I'm already working on it. Fortunately, he was able to come up with the solution before the duel and dominated the less experienced Fiore. This battle has gone viral, and a mathematician named Cardano heard the news, asking for Tartaglia to share the solution. Hey bro, I've heard that you won the duel for the press cubic. Walk in the park. Can you share to me your solution? Okay, but promise to tell no one. You can trust me, bro. Cardano then kept the solution in secret for the word of honor with Tartaglia. A day has come that Cardano learned that Del Perro is the first to come up with the solution, so that he felt he will not violate his word with Tartaglia. He then published the solution and started to work on it, but found out that a certain equation, x cubed equals to 15x plus 4, breaks the solution, having a square root of negative numbers on the roots. Cardano says, it's a crap, rubbish, and Cardano stopped working on it. A young mathematician, Rafael Bombelli, a follower of Cardano, continued the works of Cardano with a paradigm shift. Bombelli says, I will treat the square root of negative 1 as another number. Check if it behaves like a real number. He was the first to discover the solution to Cardano's unfinished business with x cubed equals to 5x plus 4. Bombelli assumed that a root exists for a cubic polynomial in the form of a plus minus b square root of negative 1, including negative 1 as a new number. Bombelli equated it with the Cardano's cube root equation and found a real number solution without the square root of negative 1. He then cleverly approached a trial and error technique to see at least one valid root. He found it to be equal to 4, and when he substituted this value in his form of a plus minus b times the square root of negative 1 as a root, it was validated to be conforming to each other. Finally, a eureka moment. He found a solution to x cubed equals to 15x plus 4 equation. So what do you think Bombelli did upon this discovery? Bombelli documented all of his work but never published, as he thinks it was all just using fallacious argument and an act of deceiving. Little that he knew, and thanks to Bombelli, his paradigm shift of accepting square root of negative 1 as another number turned out the discovery and introduction of a complex number. And square root of negative 1 is so crucial in our complex analysis and process. The work of Bombelli about square root of negative 1 has been known for many mathematicians, but a lot of speculations if it really does exist. Hence, square root of negative 1 was given a very terrible name, imaginary number. And a number in the form of combined real and imaginary part is now called a complex number. A little over 200 years after Bombelli, Euler is working in a multidimensional mathematics analysis and find the square root of negative 1 as a crucial part in his analysis. He denoted square root of negative 1 equals to I, as we know now. Gauss, on the other hand, is working with polynomials and discovered that polynomials has complex roots as well. Now that we know how the complex numbers came about, let's see its geometric representation. A complex number denoted by set equals to a plus bi has a real and imaginary term that can be represented in a Cartesian plane. Instead of x and y that are both real numbers, we will have real part in the x-axis and the imaginary part in the y-axis. We will call it a complex plane. We can represent a complex number as a point in a complex plane, with a and b as our coordinates. We can determine the position of the point by traversing along the real axis with the number of unit steps of the real part, then followed by a unit step in the imaginary axis. Example, set equals to 3 plus 2i. We need to travel 3 steps along the real positive axis, followed by 2 steps in the positive imaginary axis. Another example is 2 minus 3i. We can also represent a complex number in the vector form having a modulo r as the distance of complex number from the center of the complex plane, and an argument theta that determines the angular difference from the real axis. It can be written as z equals to r times e to the plus minus I theta. You may recall from the Euler's identity that e to the plus minus I theta is equal to cosine theta plus minus I sine theta. Please take note of the Euler's identity as it will become handy on doing some problems with complex numbers. You will observe that a relation of real and imaginary number in the complex plane forms a 90 degrees angle, and therefore we can use Pythagorean theorem to determine the absolute value of r, and the angle of displacement is given by the relation tangent theta equals to b over a. In this example, 4 units of real part and 3 units of imaginary part will give us modulo of 5, and theta equals to 36.87 degrees. Then we can write it in the polar form z equals to 5e to the I 36.87 degrees. In the same way, we can represent it as z equals to 5 cosine 36.87 degrees plus 5 I sine 36.87 degrees. Next is just to show you the different forms that we can represent a complex numbers. First, in a rectangular form, second, in a polar form, and third, as a point in a complex plane.